Today we're going to take a look at representation of functions by power series. And one of the functions that we have seen, the series that we have seen so far is going to be super important in what we're doing today, and that's the geometric series, which you all liked, right? Yes, you did. And it had a really, really nice feature at the end of the geometric series that said if it converged, it had a closed form way of finding what it converged to. Do you remember that?
Yeah.
What was that equation or formula or whatever you want to call it? A over 1 minus R. So what we're going to talk about today is going to hinge very heavily upon that. All right? So let's write down a few facts of what's going on here. So we're going to consider a particular kind of function. Style this out. So consider the function let me give it a name first, f of x equals 1 over 1 minus x, which closely resembles the sum of the geometric series summation from n equals 0 to infinity of a r to the n, which you guys just told me summation is a over 1 minus r. It looks similar, right? Yeah, that function looks similar. In particular, one more thing is that that of course only holds when the r value is between 0 and 1. Of course, otherwise that formula just doesn't give you a value that makes any sense. It's inappropriate. Okay, in other words, there should be. It sounds like there's something that there should be, but I don't know of one. For a equal 1 and r equal x, we can say that 1 over 1 minus x equals the summation from n equals 0 to infinity of a to the r, a times r to the n. And using those values, this would be n equals 0 to infinity of x to the n. A is 1, r is x, we would end up with this. So what you see, if you consider the outer edges of this, is that we have now a function represented as an infinite series. Okay? Just as a sort of reminder, this is actually the series 1 plus x squared plus all the way out, as long as the absolute value of x is less than 1, right? Otherwise it doesn't make sense. Geometric series, things going on here. If the series is outside, or is centered, I'm not outside, I was on the wrong line, is centered elsewhere, this one would be centered at 0, right, because that's halfway between -1 and 1. If it is centered elsewhere, a different series must be developed. So that's what we're going to do. We're going to center our series in a different location and see how we would use this information with that instead. I think I have enough space to at least start on this screen, maybe enough to finish it. All right, so here's an example we're going to do. We're going to find a power series. For the function centered at C. And the function we're going to use is 2 over 6 minus x with a C value of -2. Okay, so my goal is to get it to look like the geometric series, a over 1 minus r. So we're going to be manipulating, this is algebra, right? So we're going to be manipulating the function that we're given to have that feature. But we also have to manipulate it in such a way that it's centered at c equals -2. So we're going to start with the c equals -2 part of this and just look at the function itself. So this is nothing about series at the moment. It's just the function itself. So the first thing I need there to be a centering of this at 2. So what will that look like? Well, it means that instead of this minus x, I need it to say x plus 2 right here. Now I can't just go adding x plus 2, so we'll fix that in a second, but the x plus 2 is going to give me the centering. Okay? Did I really add 2 to the denominator? What did I really do, Kristen? I really subtracted 2 because there's a negative in front of that parenthesis, right? So to compensate, think about like what we did when we complete the square. I need to add another 2. Okay, because I really subtracted 2 from the denominator. I'll add 2 from the denominator to compensate. And if I clean that up, of course, I can combine the 6 at the beginning with the 2, so I have 8 down here. Okay, so far so good? Okay, but I don't want that to say 8. What do I want it to say? I want it to say 1. So I'm going to have to actually get it to say 1 by using division or multiplication with fractions. So in particular, what I'm going to do is I'm going to multiply numerator and denominator by 1/8. Right? So now I'm going to have a 1/4 on top. That's okay. There's nothing wrong with that. I've got the desired 1 right here. And then I've got x plus 2 over 8 in the place of where the r would have been. Okay, so identify for me. What is the a value here? If you're comparing this to a over 1 minus r, right? What is a? 1/4. And r is what? It's x plus 2 over 8. Okay, everybody good so far? Okay, cool. So let's actually go back to, all right, let me just make this a little smaller and we can keep using my screen. That's one of my favorite features here. Wish I could do that on chalkboard. Move things around like that, super fun. Okay, so if we're going back to this series notation now, what this means is, of course, that this is going to equal my 1/4. Well, you know what, I'll rewrite it this way. 2 over 6 minus x, which we have found is also equal to 1/4 over 1 minus x plus 2 over 8. Is going to equal the series from n equals 0 to infinity of a, which we said is 1/4, times r, or x, r, which is x plus 2, yeah, over 8 to the power n. But there is one more thing that we need to be aware of, and we saw it happen up here. There's a radius of convergence going on, right? It's 1 on either side of the only way this works is if we're in the interval from -1 to 1. So we need to make sure that our R value here is still between that. So in particular, we have -1 less than x plus 2 over 8 less than 1. And we're going to solve that inequality. So we'll multiply by 8. I keep wanting to make it less than or equal to. That is not what it is. X plus 2 less than 8. I subtract a 2, and what will I get? Yep, -10 to 6, and that would be my interval. So my interval of convergence, the only interval upon which this even makes any sense to talk about in this way, would be between -10 and 6. Yes?
We don't test the endpoints of this, right?
We don't, because we're using the geometric series. So we're going to see one a little bit later where we're going to test the endpoints, but there's a different thing going on. Yeah. Yeah, because it won't converge if it's equal to 1, right?
Right.
Yeah. Excellent question. So the answer to my question actually is over here, right? It's this series along with the interval of the convergence, because otherwise we can't make the claim that that's the series. All right, there's some lovely operations with power series that allow us to extend this idea a little bit further. Does everybody have everything okay? And can I switch slides? Okay. So these are operations with power series. So let f of x be the sum from n equals 0 to infinity of a sub n x to the n, and g of x be the sum from n equals 0 to infinity of b sub n x to the n. The first fact is that if I have a function of k times x, and I were to distribute this through kind of an idea, this summation would be n equals 0 to infinity of a sub n, k to the n, x to the n. Which should seem reasonable. If I replaced x with k times x, both the k and the x would be raised to the power of n, right? All right, second one. I'm using the notation of your book. That doesn't mean I like it. X to the power n, it is a capital N, because we've already got a little lowercase n going on. This is the summation from n equals 0 to infinity of a sub n, x to the lowercase n times capital N. Raise your hand if you love that notation. I'm not a fan. Okay. We could. I was just using what your book used so that it was consistent. You know, we'll go back later and be like, why'd she use a K? Well, yeah, K would actually make it a little bit friendlier. So, oh well. They are representing here that n is a constant, so that may also be why they're using a capital as opposed to the lowercase n, which is something that's sequentially increasing, right? N is actually a constant here. So the third one is that if you have the sum of these two functions, or the difference, then this is actually the same as having, a sub n plus or minus b sub n times x to the n. And again, that should sort of feel like we agree with that. There is one caveat to this that you do need to be aware of, so this is my note about this. These properties can change the interval of convergence. I'm just going to give you a real simple, quick kind of example so you can see what I mean by that. This isn't like a real answer, a real interval, but if we had n equals 0 to infinity of x to the n, this one's interval of convergence would be negative 1 to 1. We already saw that actually. That was our very first example today. Okay? And if we added that to the summation from n equals 0 to infinity of x over 2 to the n, we would actually have an interval of convergence here that's negative 2 to 2. Okay, so nothing says that I can't do this addition. I can do it, it's okay, but the interval of convergence obviously can't be both of those things. So what happens? Well, it's actually just the intersection of the two intervals. So we would get the summation from n equals 0 to infinity, that's totally fine, of 1 plus 1 over 2n if we were to add them together to the x times x to the n. Okay, I'm just adding the two functions or the two insides of the series together. It would actually be negative 1 to 1 as my interval of convergence, and what it is it's the intersection of the intervals. It's important that we describe it that way because it's not just the more restrictive of the interval, because potentially these could overlap and not even be one nested inside of the other one. This one's nested, right? Negative 1 to 1 is inside of negative 2 to 2. So it makes sense to talk about the smaller one as being inside of it. But if these were overlapping intervals, like it said negative 1 to 1 and 0 to 2, what would we end up with our interval of convergence being? 0 to 1. Yeah. So be aware this is the intersection of the intervals. Okay, so we're going to try another one, kind of like the one we just did. Same directions with one extra piece, but it's really a part of the directions anyway. From a 4, find a power series. And the interval of convergence. I am abbreviating it IOC, okay? And the sequence we're going to, or the function rather, that we're going to look at on this one is h of x equals negative 2 over 1, x squared minus 1. Now, this doesn't really look like that a over 1 minus r, not near as clear as the last one, because I've got something squared, right? And your book's actually quite friendly. It's not going to make you do this, but the reality is that you could use partial fractions to separate it. But again, it's super friendly and it's done it for you. So yay for the book, right? Yay, because we assume you know how to do it already. So this is actually the same as 1 over 1 plus x minus 1 over 1 minus x. So this is actually a sum of two functions, and those two functions both look like the geometric form we had before. So we can independently work with each one of those, and then according to what we just did with the operations on the previous slide, we should be able to combine them, in this case with subtraction, right, and use those properties. So let's take a look. We'll start with the 1 over 1 plus x. So on this one, I need for it to be, my eyes, I need to bring my glasses and I keep forgetting them at home. All right.
Are we sure that's right up there?
Are we sure that's right up there? Well, I copied it out of your book, so I'm pretty sure it's right. I mean, like, they make mistakes too. We can check.
Did they skip a bunch of steps? Because the way I'm seeing it, cross multiply, it doesn't make sense.
It's partial fractions.
Yeah, it's partial fractions. Yeah, it's not, that's true. It's not, yeah, it's partial fractions.
Okay,
Yeah.
That's just seemed right for a second.
Yep, that's okay. It's a good question to ask because, you know, I could definitely make a mistake. You guys see me do it all the time, right? You don't have to answer that question. No, never. Okay. All right, we're dealing with the 1 over 1 plus x part. And this actually can be rewritten as 1 minus negative x. Okay, I need it to look like that 1 over 1, I'm sorry, a over 1 minus r, right? So I can do a double negative, and that's okay, we can do that. Which means that I can rewrite this, oh wait, I'll write it down there, just for this benefit. We've got a equal 1, what would r equal? Negative x, okay, cool. And so we can rewrite this then as the summation from n equals 0 to infinity of 1 times the r value, which is negative x, to the n. And actually, Shane and I were talking about one where you had it written like this a little bit in your book, with that one that you mentioned in my office, and you're like, how do I know that this is happening? It's not an alternating series. So when you have a negative quantity raised to the power of n, you could separate it, right? So this could actually be rewritten as negative 1 to the n and then x to the n, right? Okay, very good. And what is my interval of convergence on this? Still negative 1 to 1, right? I mean, it didn't change anything. That negative on the inside doesn't switch anything. So it's still negative 1 to 1.
Yeah, don't you find it by the root test also?
The interval of convergence? Yeah, I was still doing geometric series. So you can find it by the root test. You're correct. In fact, interestingly enough, the grader contacted me and said, your students use the root test, some of them on this one, and you use geometric series. And there's another one that was a ratio test, and I used geometric series. So there's places where there's multiple options. So yeah, you could. Yeah, cool. All right, so how about the other function? I have 1 over 1 minus x. That one's even more straightforward, right? A is going to be 1. R is simply x. So this one is equal to the summation from n equals 0 to infinity of just x to the n, right? And these do actually happen to have the same interval of convergence, right? Negative 1 to 1. These two. All right, so when I look at finding negative 2 over x squared minus 1, which we have changed to being 1 over 1 plus x minus 1 over 1 minus x. And I now have the summation from n equals 0 to infinity of negative 1 to the n x to the n, minus the summation from n equals 0 to infinity of just x to the n. According to the third property that was listed over there on this slide, right, I should be able to combine both of those coefficients and multiply it by x to the n afterwards. So if I do that, I feel like I'm running out of space down here, so I'm going to move this. If I do that, I have the summation from n equals 0 to infinity of negative 1 to the n minus 1 times x to the n. So, man, that looks ugly, doesn't it? It really does. And the reality is that we can clean it up a whole bunch if we just look at a few terms, okay? So we're going to write down a few of the terms of our series, see what the sequence would look like if I wrote down the first. We'll notice a pattern pretty quick. And find a better way to actually write that than this, because that looks terrible. Okay, so I'd like for you, pause for a moment, I'd like for you to find out for me what happens when n equals 0, n equals 1, n equals 2, n equals 3, until you find a pattern, okay? So I promise you're not going to have to go that far. So I'd like for you to evaluate this at n equals 0, 1, 2, 3, 4, I think 5 will be enough actually. So if you plug in, we'll do the first one together. If you plug in n equal to 0, what is it going to equal?
1.
Just 1, right? Yeah? Negative 1?
0. Negative 1 is 0. Does it equal 0 because when negative 1 is 0, it's
Well,
1.
okay. But I've got negative 1 to the 0 minus 1 times x to the 0. So this is negative 1. Oh, this part is 0. Is that what you're saying?
Yeah.
Ah, yes, I'm with you. Okay, good.
Which makes the whole thing.
Yeah, so this whole thing's 0. Fabulous. Okay, so this one's 0. Yep. So try it for n equal to 1 and after that. What did we get for n equal to 1? Negative 2x. Okay.
0. All the odds are 0. I mean, the evens.
All the evens are 0. That's already good news, right? Okay, so we have negative 2x for n equal 1. What's n equal 3? What is n equal 5? Ooh. Do you see a pattern? Yeah, I told you it was going to come about pretty quickly. Okay, so taking a look at what you have here then, you've got negative 2x minus 2x cubed minus 2x to the 5th. And of course we intend and expect this is continuing, right? I mean, we can see what's happening with our values. So we'd like to write this in a different way. Well, clearly there's a negative 2 going on, right? Okay, so I've got a negative 2. I'm going to write that in the front of the summation because they're all multiplied by negative 2. 0 to infinity of what? What is going on? What kind of powers of x's am I getting? Yeah, and so I'm getting odd. So this is x to the 2n plus 1 or 2n minus 1. Do we want minus? Yeah, I think we want minus if we start. No, we want plus if we start at 0, don't we?
We start at 1.
No, we start.
It's written right now to start at 1. If you started at 0, I mean, it's written right now to start at 0. If you started at 1, then you'll have minus. That's just another way of expressing it, which would be totally fine, David. So we have this. You guys good with that? Odd numbers are 2n minus 1 or 2n plus 1. Even numbers would just be 2n's. Okay? So this would be our sequence. Sorry, series. Get the right word in there. And the interval of convergence is going to be negative 1 to 1, right? And again, kind of like Bryson asked earlier, we don't have to test that because we're using the geometric series, and that's already told to us that the negative 1 and the positive 1 would give us an R value that make it not equal like this, right?
Wouldn't our old answer still count on this thing? That's the answer if we were going to like any other end, but we could still answer the negative 1n minus 1 times xn.
We're going to clean it up when we can. Okay, so we're just simplifying. It's just like simplifying expressions, kind of like when you're working with derivatives and on the quizzes you guys are doing, of course, I'm going to let you leave it as 3 times 2. But if you really left something as 3 times 2 on a test for me, I probably would roll my eyes first, and then I'd take off like half a point because really you should write it on a 6 kind of thing. Okay, Shayna?
So should we always plug in?
If there's a way that you feel like there's got to be a simpler, cleaner way to write that, then yes. You don't. I mean, when you if you had stopped, like let's say for instance that let's go back over here to number 1, where we had gotten it down to this point down here at the bottom. You can leave it like that because there's not going to be a nice way to clean that up because part of it's raised to the power of n and part of it's not. Like, could I put the 1/8 or 1/4 in front? I could, but everything else is dependent upon a power of n. But if you take a look at the negative 1 powers, one more over here. Negative 1 to a power of n is either going to be 1s or 0s, and so that's why things are canceling out and cleaning up very nicely. So, okay, a little bit different. We're going to kind of switch gears a bit. Another method for finding power series is by differentiation. And integration. Or integration, I could say, but yeah. So the directions are going to remain the same. Determine a power series. And the interval of convergence. And we're going to do one f of x is 2 over x plus 1 cubed. And again, we're going to get this sort of, I want to say handed to us on a silver platter a little bit. So what I want you to see is this. This is actually the second derivative of 1 over x plus 1. Rational functions kind of have this weird thing where when you take derivatives, right, the denominator, think about quotient rule, right? You square denominators and then things cancel out with numerators and you end up increasing the denominator's power when you do that. So this is actually the second derivative of 1 over x plus 1, or 1 plus x if you prefer. And we actually have a form from exercise 2, so, or from example 2 that I did above. We saw this, this series. So in particular, the 1 over x plus 1 actually was the summation from n equals 0 to infinity of negative 1 to the n, x to the n. We did that already. Okay, so please don't reinvent the wheel if we already did something. Use what we've used and go from there. If I ask you to show it for that one, that's different, but you're going to use it from here, okay? So what does this mean? Well, this is kind of a fun one. So we're going to actually take the derivative twice, otherwise known as the second derivative. So we've got the summation from n equal, and think about what happens when you work with polynomials. When you work with polynomials and you take a derivative, you lose the constant term, right? If there's a constant term there, it disappears. And in particular, when we do antiderivatives, we've got to do a plus c on the end, right? So the way that that affects series when we work with them is our limits of integration, the lower summation value changes. So this is actually going to start now at n equal 1. When I take a derivative, it will change from n equals 0 to n equal 1. And I'm going to take a second derivative here in a moment. It's going to do it again. Now, in the very end, we're going to reset it back to 0, but in the midst of what we're doing, it's changing the lower counting limit. So take a look. What is the derivative? Well, this is just a constant, right? Negative 1 to the n is a constant. So derivative with a constant, the constant stays the same. What is the derivative of x to the n? N's a number. X is a variable. You got it. Nx to the n minus 1. And hopefully now you see why also we had a change in our n value. If n were still starting at 0, we would no longer have a polynomial on the right-hand side, would we? No, we wouldn't. Okay, so we're going to do the second derivative. We're going to do it one more time. So my summation now will start at 2 to infinity. The coefficient, negative 1 to the n, and the n are coefficients, now they're going to stay. What's the derivative of x to the n minus 1? Good. So this is kind of back to Ethan's question before, is, how could I just stop here? Have I found this sort of a series? And the answer is I have found a series, but I can clean it up. In particular, I'm going to reset it back to n equal to 0 at the bottom. So what's going to happen when I have to reset it to n equal to 0 is that I'm shifting all of my n values. How am I shifting them? We haven't done a lot of this. We did it a couple of very specific times along the way because we're working with geometric sequences, right? And they start at 0. And so we had to shift them a little bit if something started at 1 and we need to move it back to 0 to find the summation or something like that. Okay, yeah, we could do that. The other thing that you can recognize is you could actually see what happens when you plug in n equal to 2, right? So when I plug in n equal to 2, the negative 1 to the n I'm not concerned with, but the n equal to 2 here would give me a 2 here, right? Like the n value would become 2. So what would it have to actually look like? Let me rewrite this part of it since it's I just said to ignore it. What would this have to actually be to give me an n equal to 2 here if I plugged in 0? It would have to be n plus 2. That's my shift. How about the n minus 1? What will it become? N plus 1. And then x to the n minus 2 will become x to the n. I'm adding 2 to all of my n's because I took 2 away from the lower n equals 2, like the lower limit of this series.
We didn't have to do that with a negative 1, obviously, because we didn't do that with a negative 1 at the end.
Because we weren't finished. Oh, because that we didn't have to do it because it's an alternating series? Yeah. Yeah, because it just goes back and forth. Yeah, you're right. Okay. What about our interval of convergence? We found our series. What's our interval of convergence? Still negative 1 to 1, right? You use the geometric series that was involved here, right? Same thing. So
negative 1n times n plus 2 times n plus 1, that's a.
yes, it would be. Okay,
The geometric series.
we used it back up at the beginning, very, very beginning, right here. Yep, good question. Kind of hidden in there, right? We used it from a previous example.
So how do we know to go down to the second derivative?
It told you. The problem here said second derivative. It was actually given that way. So this whole question is how the question's posed. Yes. Okay. So I told you we could use differentiation or integration. So we're going to use an integration one now. You ready? Don't get too excited. No. Okay. Here's my integration one I want to show you. Here's my function. F of x equals the natural log of x plus 1. So again, Shane, it kind of along the lines of what you were saying, this is how the problem starts out. All of what I'm writing right now is the problem. Okay, so I'm stopping right there. That's the question. All right, so we're going to be able to do the same thing we did before. I have, again, with like Becca asking, where do I see the geometric series? It's right here, right? The 1 over x plus 1 part. Okay, so we're going to rewrite that. Whoops. Is the summation from n equals 0. Hang on, I left my integration symbol off. Let me move it over a little bit. Here we go. From n equals 0 to infinity of negative 1 to the n, x to the n. There's the dx at the end. Right? And we're going to allow our integration, just like I did the derivative, to pass through inside of the summation. So I have the summation from n equals 0 to infinity. Negative 1 to the n is a constant. It doesn't change anything. What's the antiderivative of x to the n? X to the n plus 1, right? Over n plus 1. Oops. But I did an antiderivative plus c. Good job. We got to figure out what c is. That's our next step. Okay, so far, my interval of convergence still seems like it's this, right? We're going to come back to the endpoints on this one because the endpoints on this one do change a little bit because of what's going on. So to solve for c, what we need to do is we need to recognize that we have an equation here. We have an equation that says the natural log of x plus 1 is equal to the summation from n equals 0 to infinity of negative 1 to the n, x to the n plus 1 over n plus 1 plus c, right? This is an equation. We just need to figure out what c is. And when you did this for, Calc 1 the first time you would have seen it probably, you were given, if you were supposed to find c, you were given what was called an initial condition. And they told you some function value things that you could plug in and you could figure out what c is. And we have a similar kind of thing going on here. We aren't given anything because we don't need anything. We're just going to let x be a specific value, and it's very nice to let x equal 0. So if I let x equal 0, then I have the natural log of 1 on the left. What's the natural log of 1? Fabulous, it's 0, right? And then what happens right here if x is 0? It's 0, right? Because I have just x is 0 raised to the power multiple times. 0 raised to anything 0, right? And then plus c. So what is it telling me c is going to equal to? It's actually equal to 0 on this one. Of course, that doesn't always happen, but it was on this one. No, you don't. You can leave it off now that you've identified and found it. So this is a summation from n equals 0 to infinity of negative 1 to the n over x to the n plus 1 over n plus 1. Oops, and I said no plus c, so it's like that. That's a good question. So we actually have something a little bit weird happening on this one. This is an alternating series, right? And we've talked before about the fact that alternating series can converge on their endpoints, right? And in fact, alternating series are really very friendly because all you have to do is you have to see whether the part that doesn't have the negative 1 to the n approaches 0, right? To see what would happen. So pause with me for a moment and consider what would happen at the endpoints here. I mean, it's an alternating series. If I were to have an endpoint of 1, this would be 1 over n plus 1, right? Ignore the negative 1 to the n at the beginning. If n is equal to, if x is equal to 1, I get 1 over n plus 1. Agreed? Because I have 1 raised to powers, but it's just going to be 1. This is going to go to 0, right? Okay.
Not to be nitpicky, but shouldn't it be negative 1?
So I'm doing like this. That's what I was considering. Yeah, is the limiting part of it, okay? So if I plugged in 1, I'm going to end up getting 1 over n plus 1. What if I plug in negative 1? Well, there's a negative 1 to the n here, right? And if I put another negative 1 to the n, what's going to happen in the numerator? It's just going to be 1. And in particular, I don't have an alternating series anymore, do I? No, this is no good. I mean, we got n plus 1s, whatever. But yeah, this one is not going to alternate, right? So this one is not an alternating series.
Wouldn't it always come out to negative 1?
On top?
Yeah, because negative 1 to 1.
Oh, yeah.
Uh-huh. Yeah, but it won't alternate, is the point. It still won't alternate, yeah. Yeah, so on one of the endpoints, it alternates. So the fact that it alternates and it's harmonic, right, is enough to say that it's still going to converge because it's alternating. But on the other endpoint, it's not alternating. So it's alternating harmonic, which means it diverges, right? So on this one right here, because it's alternating with the limit approaching 0, it will converge when x is equal to 1. But it won't if x is equal to negative 1. So take a look here. So in particular, that means my interval of convergence actually includes one of the endpoints. It doesn't include negative 1. It does include positive 1. And you might be thinking, well, why didn't we worry about that on the last one? So I want to flip back over and show you why. Are you ready? Take a look at this one. I don't have denominators, right? I have n plus 2 and I have n plus 1, and they're both going to infinity. So even though this is an alternating series, the rest of it, ignoring the alternating part, does not approach a limit value of 0, right? Are you with me?
Yes.
That's why it didn't come up here. So should we have checked it? I probably should have. I should have probably mentioned it then, but I knew I was going to mention it now. Okay? So this one did not have, the rest of the sequencing actually having a limit approaching 0, so the alternating series test didn't actually help us to know that it converged. It diverged at those endpoints. Okay, sorry, let me get you homework so you guys can head out. Right up here at the top. Page 662. Numbers 2, 5, 8. 11, 18, 19, and 22. Not very many, right? Not very many. All right.